This video is going to cover misclassification calculations, and these are calculations that let you correct for misclassification if you know something about sensitivity and specificity of what you use to classify people as exposure positive or negative, or disease positive or negative. So this is basically the setup for sensitivity and specificity, where we have this test that is testing whether someone's disease positive or negative, and we have their true state here, which is either a gold standard or just what they actually are. And our test can agree with the truth, so we can have true positives and true negatives, but they can also disagree based on whether someone, or at least us saying that they're disease negative but they're really disease positive, so false negatives, or us saying that they're disease positive when they're really negative, and that's a false positive. And yeah, so this is basically misclassification, incorrectly specifying someone's disease or exposure status. And for the rest of the video, we're going to focus on misclassification of exposure. The same rules kind of apply to misclassification of disease, but the calculations are easier to show when one is assumed to be held constant and true. And this is just it with numbers. So sensitivity is the probability of testing positive given that you're disease positive. So it's pretty much just the proportion of those disease positive that we found. So here it's 55 divided by all the disease positives, and that's 93%. So that means that we found 93% of those that are diseased and correctly identified them as such. So higher sensitivity, fewer false negatives. Specificity is the probability of testing negative given that you're disease negative, so it's kind of the converse to sensitivity. So that's the number of correctly identified disease negative people out of everyone that's disease negative. And that should have been specificity, whatever. But yeah, so specificity is basically 70% here, and that's pretty bad. That means that we only correctly identified 70% of those that are disease negative as disease negative, and we had a lot of false positives. And higher specificity means fewer false positives. So this is our case control example. Notice that this changed. This is now cases and controls, so disease positive and disease negative, and this is now exposure. So this isn't anything about the test. So with case controls, you're typically measuring exposure in the past, and when we do that by like asking them whether they were exposed and asking them to remember, and there's a lot of opportunity for misclassification here, and there's two ways that misclassification can happen. Someone that's exposure negative can be put into the exposure positive group, and someone that is truly exposure positive can be misclassified as exposure negative. And cases and controls both have their own independent sensitivity and specificity. So whether your case or control might influence your likelihood of being misclassified. This is kind of common, like recall bias is an example of this, where cases might be thinking harder about why they became a case and might either remember their exposure status better than a control because they've really been thinking about it and are able to trace back all of the harmful things they've been exposed to, or they might be searching for the reasons that they have the disease and might say, oh yeah, I was exposed to this, when really they weren't, just because it makes sense to them that they think they were, because they're trying to explain why they have the disease. So yeah, misclassification might be more or less common among cases and controls. So non-differential misclassification is when sensitivity and specificity is the same among cases and controls. So both cases and controls are equally likely to remember their exposure status correctly or incorrectly. And differential is when the sensitivity and specificity of exposure classification differs whether you're a case or a control. So when we know sensitivity and specificity and we have some results, there's a few things we can do. We can go from the true results to the observed, so completely correctly classified to incorrectly classified. We can also go from what we've observed and correct to get true results if we know sensitivity and specificity. So this is our situation. We have cases and controls. These are the results of a case control study. We have 100 of the cases that were exposure positive, 75 that were exposure negative, 210 of the controls exposure negative, and 320 210 that were exposure positive that were controls, and 320 that were exposure negative. And this is illustrating non-differential misclassification, so sensitivity and specificity are the same for cases and controls. So just going through what this true odds ratio is, so 100 over 210, 75 over 320, we have an odds ratio of 2.03, so if you're exposed, your odds of being a case are about 2 times higher. But we know that among cases, the sensitivity is 0.9, so 90% of these 100 people are really exposure positive, but 10% are really exposure negative. So we can use that 10% that we know are here, that we're really supposed to be here, and say that represents 10 people, and we can say that 10 people should be moved down here to get what we're going to observe. And with specificity, we know it's 80%. Going through a similar idea, we know that 80% of these exposure negative people are really exposure negative, but 20% should be up here. So 20% of this 75, 15 people should be moved up here. We can do the same thing for controls, where we have a sensitivity of 90%. So 90% of the 210 should really be here. 10% belong here. So 10% of 210 is 21. So 21 people should move down here. And just like before, 80% for sensitivity. So 80% of this 320 people belong here. 20% belong here. So 20% of 320 is 64. So 64 moves up here. So now that we know, now that we're not correcting misclassification in this case, we're going from truth to observed. So taking into account, like for this 100 that is losing 10 and gaining 15, if we do that for everyone, I'm not going to go through it, we get these observed values, and the observed odds ratio is 1.64. And notice that that's closer to the null value of 1 than our true odds ratio. That leads us to a constant. I've only shown you one example, but you can believe me when I say that regardless of the rate of mixed classification, if it's non-differential, if it's the same among cases and controls, it's always going to dilute the effect towards the null. And that's a bit of a less insidious, depending on like what your priorities are, that's a bit of a less insidious bias where you're less likely to discover a false trend, and this non-differential misclassification is just going to make your results less significant, even if there really is a trend there, which I guess in my opinion is less insidious than reporting a false result. Differential misclassification occurs, like I said before, when the sensitivity and specificity differs depending whether you're a case or control. So in this example now, for the cases, everything's the same as it was before. We have the same initial truthful table, but for cases, everything's going to be the same. But for controls now, we have a sensitivity of 95% and a specificity of 75%. So the true odds ratio is going to be the same, and so will this first half, everything for the cases, because it's the same as before. But for controls, now just going through everything we did before, we know that of these 210 exposure positive controls, 95% belong there, 5% don't. So 5% of 210, 10.5 go down here to exposure negative. And same thing with this sensitivity of 75%. There's 25% of these 320 don't belong, so 25% of 320, 80 go up here. And taking into account all this again, I'm not going to go through it. We end up with a new distribution here where our observed odds ratio is 1.34, so it was attenuated, but I'm going to show you how it could have gone another way. So here now, before sensitivity was 95% and specificity was 75%. Now sensitivity is 75% and specificity is 95, so we switch to those. And let's see what happens. Case, same thing's happening here. But now, sorry, now we have, for sensitivity, 75% of this 210 is correctly specified, 25% doesn't belong, so 25% of 210 is 52.5, so they go down here. And for specificity, we know that it's 95%, so 5% of this doesn't belong here. 5% of 320 is 16. And taking all that into account, the new distribution, we have an observed odds ratio of 3.08. So now we've shown that depending on whether, when there's non-differential, when there's differential misclassification, depending on whether sensitivity or specificity is higher, the odds ratio can be attenuated or made more extreme. So it's harder to predict what the effect is going to have. Where with non-differential, we're pretty confident that it's always going to attenuate. So far we've been going from the true distribution to the observed, but it's also possible to go from observed to truth. So for this one, when going from observed to truth, you work with probabilities of exposure first, and then you're able to use that to come up with the number of people in each cell. So for this formula, to find the true probability of exposure, we take the observed one plus the specificity in cases, and remember, this is specific to cases. You do it separately for cases and then again for controls. So yeah, observed probability of exposure in cases plus specificity in cases minus 1 over the case sensitivity and specificity added minus 1. And for controls, it's the exact same formula basically, but you're just using the control information. So now, basically, this is the table from our non-differential misclassification example. This was what we got to when we went from truth to observed. I'm going to show you how we can go from this back to what we started with. For this true probability of exposure in cases, basically we have all of this information. We know sensitivity and specificity, but we need to figure out the probability of being exposure positive if you're a case. So that's 105 over all of the cases, so it comes out to 0.6. And we can do the same for controls. The reason I didn't keep I only kept one decimal here and kept so many more here is because we're working with bigger numbers over here, and I needed to do that in order for it to come out to literally the result we got, the result we started with. Otherwise, it accumulates error, and so we're gonna keep this many decimals. So when we figure out the probability of exposure in controls, it comes out to this. Now we can get the true probability in cases. We have everything now. We have the case sensitivity and specificity, because we know it's the same for both cases and controls, so we have both. And that, when we plug all that in and figure it out, the true probability of exposure in cases is 0.57. We can do the same thing for controls, so observed probability of exposure in controls, plus everything's the same pretty much for these two calculations, except for the probability of exposure. And then true probability of exposure, again, keeping all these decimals so we can actually get the right number. So now I got rid of, because regardless if it's true or observed, this margin is going to be the same, because if you remember, stuff's just moving up and down within this column. These columns don't interact with each other. So yeah, the marginal total is going to be the same. So we have the true probability and we have the marginal total, so we can figure out how many people should be in these two cells. So the true probability of exposure of 0.57, and with 175 people, 99.75 people belong here. Can't have a fraction of a person, so we round up to 100. And since we know 175 are there and 100 are here, we can figure out that 75 belong here. And we can do the same thing with controls and come out to 210 and 320. And that's the result we began with. If you don't believe me, you can go back and look. But yeah, you can take my word for it. We went back correctly from observed to truth, basically. Yep.